So we're on page 88 and we're going through problem 1. We're always going to split our sketches into a before and an after picture. Before is before the collision, after is after the collision. The first sentence will describe the before. We have an astronaut in deep space whose mass is 80 kilograms with an empty oxygen tank of 10 kilograms. Okay. It doesn't say they're at rest, but they don't give me an initial velocity. I'm going to assume that they are floating in deep space. Here's my astronaut. Here's my oxygen tank, and they're at rest. And therefore, if they're together and at rest, their initial velocity is 0, and their initial momentum is 0. So we can go ahead and fill in the initial part. We have the astronaut and the tank as our system. Then what does the astronaut do? He throws the tank away with a speed of 2 meters per second. With what velocity does he start to move? So we know the velocity of the tank. We don't know the velocity of the astronaut. Now, they don't say if it's moving right or left, so we get to pick. I'm going to say the tank is moving to the right at 2 meters per second. I'm just going to say it's moving right. And the astronaut, we don't know his velocity, but we do know he's moving left. Because if they're at rest at the beginning, and then he throws the tank one way, he has to move in the opposite direction. Just like our cart demo on Friday. So at the end, we have a tank of 10 kilograms with a velocity of positive 2 meters per second. So it has a positive momentum. In fact, I know its momentum. It's 20. It's 2 times 10. The astronaut has a mass of 80 kilograms, and I'm going to put a question mark here. I don't know his velocity, but I know it's negative. He has to move to the left, and I can anticipate it's not going to be as fast as 2, because if he's heavier, he should be moving slower. Okay, we saw that again in our cart demo on Friday. Now, they're never, ever going to give you force and time, but you're always going to fill it in that one is gaining and one is losing the same amount. Okay, in this case, it's the tank that's gaining momentum, and it's the astronaut that's losing momentum because he goes negative and the tank goes positive. And again, that's because they experience the same force in the same time. So the delta P, the change in momentum, must be the same. Now, let's do the math. The math is going to be initial equals final. I don't need to worry about delta P because it overall cancels out. My initial equals my final. My initial momentum was 0. So on the left side of the equation, I just have 0. On the right side of the equation, I'm going to have an MV for the tank plus a separate MV for the astronaut. The tank and the astronaut have 2 separate momentums because they're not together. I'm going to have 2 times, it's 10 kilograms times positive 2 plus 80 kilograms times my unknown velocity. Okay. So I have one momentum that's known, one momentum that's unknown because that velocity is unknown. I'm going to continue this over here. I've got 0 equals 10 times 2 is 20 plus 80 times V. Okay, this is the same equation. I'm just taking the units out to make it a little bit less confusing. I think it's easier to see the algebra here. These 2 terms, the 0 and the 20, these are my like terms. They're both momentum terms. So I got negative 20 equals 80 times V. To get velocity, I divide both sides by 80. Negative 20 over 80 is the same as negative 1/4. for negative 0.25 meters per second is my final velocity. Okay. We're gonna go through another one, but this, you're always gonna follow the same pattern. Draw a picture, fill in my IFF chart. Don't worry, draw in your delta P, but don't worry about the math for that because it cancels out. And then set up initial equals final, an equation that matches your IFF chart. The equation is gonna look different for every problem, but it's always gonna be initial equals final. Okay, this next problem is totally different because they're not at rest at the beginning. Draw a before picture with me and an after. We have two different balls. One is a 6 kilogram ball moving to the left at 2 meters per second. So I'm going to put a negative in right away as soon as I see this to the left. The smaller one, the 3 kilogram one, is moving to the right at positive 8 meters per second. Okay, again, that first sentence describes before the collision. Okay, let's go ahead and draw that in our IFF chart. The 3 kilogram one is smaller and it's moving to the right at positive 8. So I will know its momentum. It's going to be 3 times 8. It's going to be 24 kilograms meters per second. The 6 kilogram one is moving to the left at negative 2 meters per second. So it has a negative momentum. Its momentum is negative 12. Okay. You can even put in, like, I'll put in here, positive 24, negative 12. You can put the numbers right on the graph. That's fine. The 6 and 3 kilogram balls are my system. Now, that's the before. I've given both masses and both velocities. In the after picture, it says the 6 kilogram is moving to the right at 1 meter per second after the collision. So the 6 kilogram one that was moving left has turned around and moving to the right. But we're not told what's happening with the 3 kilogram one. That's because we're going to solve for its velocity. So I'm going to put 3 kilogram one and I'm going to put question mark. I don't know its velocity and I don't even know which way it's moving. It could be moving to the right of the collision, it could be moving left. Sometimes we won't know. Okay. I know that one is going to gain and one is going to lose the same amount of momentum. Think the 6 kilogram one is the one that gains because it's going to go from negative to positive. The 3 kilogram one is the one that's going to lose momentum. So I'm putting a question mark by the 3 kilogram, but by the 6 kilogram, I know that it has turned around and it's moving at positive 1 meter per second. So it has a momentum of positive 6. 6 times 1 is 6. Okay. Now we're going to set up our equation to solve, not for this final momentum for the 3 kilogram. We can figure that out, but we need the final velocity. That's our goal. Okay. So we're going to have initial equals final. I'm going to have mv plus mv at the beginning because both of them are separate at the beginning. They have their own momentums. And I'm going to have mv plus mv. Both of them are separate at the end. Okay. If I've already shown my numbers up here, I'm okay with you saying, you know, this momentum is 24 kilograms meters per second. This momentum is negative 12 because I already multiplied them up above. That's fine. This momentum is unknown. This is going to be my 3 kilograms times V. I always have to have an unknown somewhere in the equation. It's this velocity for the 3 kilogram. Plus 6 times 1 is 6. Okay. And now I'm going to do the algebra. I've got this whole equation. I'm going to solve for V. These 3 terms get combined. 24 plus negative 12 is positive 12. Okay, now I gotta combine the 6 and the 12, because those are also momentum terms. I'm gonna subtract 6 from both sides, and I'm gonna get 6 equals 3 times V. Divide by 3 on both sides, 6 divided by 3 is +2. So my answer is +2 meters per second. Okay.